All right, guys, welcome to lesson 13.4. Today we're going to learn what a period is and how to find the period of a trigonometric function. We're going to learn what a phase shift is also. And finally, we're just going to learn how to graph trig functions that have horizontal transformations. So far, all of our transformations we've been dealing with have just been vertical transformations, where you can stretch a graph vertically or move it up and down. But we're going to talk today about doing that horizontally. So first of all, let's review horizontal transformations a little bit. So if you guys have a function, and let's say you take that function and you subtract a number from the inside of the parentheses, what that will do is it will shift the graph to the left. I'm sorry, right. My bad. And if you take that function and you add a number to the inside of the parentheses, it will shift the graph to the left. This is review stuff from last fall. It's been a while since we've seen it, but there it is. All right. Another thing is that we can multiply our function. Sorry, but it's going to be inside the parentheses. You can multiply your x on the inside of the parentheses. And that's going to do one of two things, okay? If b is greater than 1, then what's going to happen is your graph is going to be compressed. So what do I mean by that exactly? Well, let's just say that the function f looks like a parabola. Well, if you multiply the x by a number bigger than 1, it's going to make your graph look skinnier. It's going to compress it horizontally. Okay? Now, if your b value, if the absolute value of it is less than 1, now both of these are absolute value. We don't really pay attention to the sign. So if the absolute value of it is less than 1, in other words, it's some kind of a fraction like 1/2 or 1/3, then the graph will be stretched. So it'll look wider. It gets stretched horizontally. Okay, so those are the kinds of transformations that we're going to look at today. So let's go ahead and do a Desmos demonstration here. So we already know what a sine function looks like, but what happens whenever I subtract something on the inside? How will it affect the graph? Well, let's go ahead and take a look at Desmos to kind of explore that. So here on Desmos, I've graphed a sine function. So what happens if I take a sine function and I subtract something from the x? Well, you guys know it's going to just shift it over, right? I'm going to subtract 45. Okay, as you guys can see, the blue line here has been shifted over from the red line. So it's like this whole line has been shifted over. Okay, and that's a horizontal transformation. Now, if I were to put plus 45, now the blue line is to the left of the original function. So the red line is the original, and now you guys can see that the blue line has been shifted backwards by 45 degrees. Okay, and so that's what that does. And so here's a summary of that fact. Now, with trigonometric functions, whenever you do horizontal shifts, we call them a phase shift. It's just a vocabulary word, not a big deal, but just letting you know. The h produces a horizontal translation. It slides the graph to the left or the right, depending on whether it's a positive or a negative. And in trigonometric functions, once again, we call that a phase shift. Now let's take a look at another situation. How about instead of subtracting or adding a number to our x, we multiply our x by something? What effect will that have on the graph? Well, you guys probably already suspect it's going to stretch it, right? But let's take a look at it. So once again, here's my sine wave. Now, let's go ahead and do sine, and in parentheses here, I'm going to go ahead and put 2x. All right, so remember how I mentioned earlier that if your b value is greater than 1, it's going to compress your graph. So my red line here is what it used to look like, but the graph got squished horizontally, and so now it's shorter. It's going up and down at a faster rate. Okay. Now another thing I want to point out to you guys is this. With a regular sine function, it usually completes its period in 360 degrees. So it starts at 0, and then by the time you're all done tracing out that S shape, you're at 360 degrees. I don't know if you guys can see that over there, but there's a little 360 at the end. All right. But now, because of this compression that we just had, look at the blue line. The blue line makes its little S shape a lot earlier. It stops at 180. So because it got compressed, the period is now shorter. In other words, the function will now repeat its cycle in faster intervals. Okay? So whenever you have a multiply your x by a number that's bigger than 1, then it's going to compress your graph and make the period shorter. Okay? But what happens if you multiply the x by something less than 1, like let's say a half? Well, now look at the blue line. The red line here was the original one with a period of 360, right? But the blue line doesn't even complete a cycle within that viewing window. We have to scoot it way over here. The blue line will not complete a full cycle now until it gets to about 720. So since we multiplied the x by a number that's less than 1, it actually stretched our graph. So now the period, instead of being 360, like it usually is for sine, 360 degrees, now it's been stretched out to 720. So just like we said earlier, when you have these horizontal transformations, if you multiply by a number less than 1, it stretches it, so it makes your period larger. If you multiply it by a number greater than 1, it compresses it and it makes your period shorter. Okay? So let's summarize that here in our notes. So if you have a trig function with some number multiplying the x, the b will compress if b is greater than 1. That shouldn't say 0, that should say 1. That's a typo. Let me fix that. Should be a 1 right there. And it stretches if b is less than 1. And I think we should also have some absolute value bars on those b's. I'll try to fix it on your guys' notes. Anyway, the b value will compress or stretch depending on the size of the b value horizontally. Okay? Now, this will change the period of your function. Okay? Now, the period of a trig function then can be found using the following formula, and that's going to be our first problem we're going to practice. So usually with sine, cosine, secant, and cosecant, the period is usually 360. But now we're going to have a b value here, which is going to change the period. And the way that it changes is you just divide the period by b, and that will tell you what the new period is. So for instance, on the last slide we were graphing sine, right? And sine has a period of 360. Well, whenever I graphed sine of 2x, it became compressed, right? Well, if I take that 2, that's my b, and I divide that, that tells me, oh, now the period's 180, so it completes its full cycle a lot faster. Okay, so that's the idea. We're going to practice that. But before we do, let's talk about tangent and cotangent. Tangent and cotangent have different periods usually. Usually they're just 180. Okay, so it's a little bit different for those two. But you still divide by b. Okay. All right, so that being said, we're ready to go ahead and jump into our first example here. All right, so for example 1, first of all, what function do we have? What trig function is this? Well, it's a tangent, right? Okay, next, what's the period of a trig function of tangent usually? It's usually 180. So we're going to divide that by the b value. Okay, so for tangent, usually the period is 180, and now we're going to divide that by the b value. What is our b value? The b value is the number that's multiplying the variable inside the parentheses. In this case, it's a theta. So my b value in this case is a 5. So if I were to divide these, I would get 3 goes into 18 3 times. So 36 degrees. So usually tangent has a 180 degree period, but because of the multiplier here, it will now have a period of 36 degrees. All right. Let's go ahead and take a look at number 2. What kind of a function are we dealing with here? Well, this is a cosine. Usually cosine has a period of what? 360. So, but what's our b value? Well, it's not 4. It's actually 1/4. A good way to rewrite problems whenever they look like this is in the following way. Instead of having it as theta over 4, we could put 1/4 theta. That way we can kind of see that the b value is 1/4. So I'm going to be dividing by 1/4 to find my period. All right. So now this is kind of different. We have a complex fraction, right? So how do you simplify complex fractions? Well, you multiply the top and the bottom by the little denominator. So I'm going to multiply the bottom by 4. So those cancel each other out. But whatever I do to the bottom, I've got to do to the top. So 360 times 4. I believe that would be 1440, if I'm not mistaken. So that's a really big period. Okay, usually cosine would complete its cycle in 360 degrees, but now it's been stretched out so much that it won't complete a full cycle and for a total of 1,440 degrees. All right, we'll do one more example here, and then we'll let you guys practice. So let's take a look at number 3. So what function is this? This is a cosecant. Usually, cosecants have a period of 360, but we need to divide it by the b value, which is 2. So if we do that, get 180. All right, we'll go ahead and let you guys practice a couple of these here. Go ahead and pause the video here and give these 3 problems a try, and when you unpause it, we'll have the solutions up for you. All right, guys, so there's the answers there. Go ahead and pause the video if you need to study what we did and how it worked out. But I'll go ahead and move on to the next part of our lesson for the day. So, how do period changes and phase shifts affect the graphing process? This whole chapter we've been talking about how to graph these functions. So how is this going to affect our graphing process? Well, as you guys know, sine, cosine, secant, and cosecant we've usually used these angles, and for tangent we've usually used these angles, and for cotangent we've usually used these angles. But if you're going to start compressing things and shifting things around, those angles are going to be changing. So for now, I'll just say what it is, but it probably won't make sense until we get to an example. But how do we change the angles? How are we going to get the right angles with these shifts? Basically, what we're going to do is we're going to take the bx plus h, which is like, so for instance, if you had this, you're going to take that piece there, you're going to set it equal to each one of these and solve for x, and every x you get will be the new angle. So this will transform the angles for you. All right, but we'll get there in a minute. I'm not going to go over this again. This is something that we went over last class, but I'm just going to include it here because you're going to probably want to reference it for today, because we're going to continue with these processes of graphing trig functions that are tangent and cotangent, sine and cosine, secant and cosecant. So without any further ado, let's go ahead and really get down to it and start graphing some trig functions. All right, so let's graph a sine function. All right, so what's the first step when graphing a sine function? If you need to look at your notes, go back to where it says graphing sine and cosine and see if you guys can figure it out. It says the first step is to set up your graph with the correct angles. But as you guys know, our angles are usually 0, 90, 180, 270, and 360. And you guys might wonder, Mr. Bailey, why are you writing these numbers all over the board? I'll show you in just a minute. Well, as you guys know, we have some transformations in here. I've got a phase shift, and I've got a period change going on there. And those things are going to change these angles. And the way that we're going to change them is we're going to take this equation, this little expression here, we're going to set it equal to the original angle, and we're going to solve, and that's going to tell me the new angle. Okay? So, minus 45 on both sides. And divide by negative 3. So it looks like my new angle, my new starting angle, is going to be at 15 degrees. Let's go ahead and do the next one. We're going to set negative 3x plus 45 equal to that also. So let's minus 45. And divide by negative 3. Negative 15. And just keep that process up. If this is boring to you and you want to just write down the answers because you got the process, I'm okay with that. Feel free to fast forward through me doing the rest of these. But I'm getting pretty close. Or if you're just doing it while I'm doing it, that's fine too. So this is really the only new part of today's lesson. The rest of it is old. So just finding these new angles that result from the horizontal transformations is the only part that's new. The rest of what we're doing is all pretty much identical. All right, so I've got my new angles here. They are 15, negative 15, negative 45, negative 75, and negative 105. And so those are the angles I'm going to use to graph this function. Actually, I think I'll draw that a little bit differently. We have mostly negative angles. So actually, I'm going to make more on the negative side here than I do with the positive. So there we go. All right, so I've got 4 angles that are negative and 1 angle that's positive. And you do want to put these in order. So negative 105, negative 75, negative 45, negative 15, and positive 15. That's it. So that's step 1. Now, I know you guys are thinking, gosh, Mr. Bailey, that's step 1. Well, yes, that's step 1. But the good news is that once you've got that out of the way, the rest of it's old news. Now, I have some other good news for you guys here. You actually don't have to find each one of these like that. All you really have to do is find the first 2 and ask yourself, how far apart are they? How far away is 15 from negative 15? Well, it's down 30. If you had 15 and you subtract 30 from it, you get 15. And guess what? It's going to be like that for the rest of them because they're all evenly spaced. So after you find the first 2, just find out how far apart they are and just keep subtracting 30 every time. So you don't actually have to solve all 5 equations. You could just solve the first 2, and then after that, you can just use the pattern. Okay? So I'll demonstrate that on our next example, but for now, we have what we have. So that's the end of step one. So with step one, with a sine function, the first thing is to find your angles, which we just did. All right, let's move on to step two. Step two is to graph your midline, which is 1. Then we're going to graph our maximum and our minimum using our amplitude. The amplitude is 1, so I'm going to go up 1, and then down 1, which is right on top of the x-axis there. Okay. Now the next thing we got to notice is when you're graphing a sine function, you have to look at your reflections. I've got a negative on the outside and a negative on the x on the inside there. So let's go ahead and go back for a second and take a look at what that means. Whenever you have a negative on the inside and the outside, your graph starts at the midline and then it goes up. So that's what I'm going to be doing there. So starting from my first angle, which is here now, I'm going to start at the midline and then go up and let the rest of the pattern fall in place. And there it is. All right. And of course, we could continue it onwards if we wanted to, but I'm really just going to be looking at that one first cycle that's there. Okay. All right. So that is, and so here's student practice 2. So go ahead and pause the video here and give it a try. And when you unpause the video, I'll have the solution up for you. All right, guys. So there's the answer for student practice 2. All right. One thing you want to make sure you got right is those angles. Did you get -90, -45, 0, 45, and 90? We get those by setting the 2x plus 80 equal to 0, 90, 180, 270, and 360. And once you set that equal to those and solve, you get the 5 results that you have on the graph over there. All right. Next, you have your midline is at 0. You have your max at 2, your minimum at -2. And since there's a negative on in front of our cosine here, we start at the bottom, the minimum, and then we go up. All right. Let's go ahead and do another example here. Let's go ahead and do a secant problem. All right. So when you're graphing a secant function, what do we do first? When graphing a secant function, you start by just turning it into a cosine function, and then you just follow the steps for graphing a cosine function. After you're done with that, you put in your vertical asymptotes and you put your little U-shapes on there. All right, so let's go ahead and do that. So step 1 here is let's rewrite it. I'm going to graph, I think I'll use another color. I'm going to graph -4 secant, no, cosine, sorry. -4 cosine of x over 2 minus 30 plus 3 equals y. And when I'm all done graphing that, then we'll go ahead and we will graph the secant function. All right, so how do we do that? Well, usually with secant, we use the angles 0, 90, 180, 270, and 360. But we have horizontal transformations. So we're going to take the x over 2 minus 30 and set it equal to our first one. And we're going to solve to find our new first angle. It used to be 0, but after I add 30 and multiply by 2 to solve for x, I now see that my new first angle will be 60 degrees. So I'm no longer going to start at 0. Now I'm going to start at 60 degrees. I'm going to do the same thing with the 90. So my second angle used to be 90. But because of my horizontal transformations, after I add 30 and multiply by 2, my new second angle will be 240. Now, we could keep doing that to find the rest of them. But I told you there's a faster way to do it, and that's just by following the pattern. These angles are always going to be the same space apart. So how far apart is 60 and 240? Well, if you just do 240, take away 60, you get 180. So these angles are 180 degrees apart. So guess what? If you just add 180, you'll get to the next one. So 240 plus 180, the next one's going to be 420. And if I add 180 to that again, I get 600. And then finally, if I add 180 to that again, I get 780. So that way you don't have to set every one of them equal to your equation and solve. You can just do the first two, find the pattern, find out how far apart they are, that is, and then after that, just keep adding that amount, or sometimes subtracting that amount, depending on whether you end up with a positive or negative. All right, so let's go ahead and do our graph. So all my angles are positive. My first one is at 60 degrees. The next one is at 240. The next one's at 420. The next one's at 600. And the last one's at 780. All right, so there's my angles. That's the end of step one. Step two, let's graph our midline. So my midline is 3. So at x equals 3, I'll draw a little midline. All right. The next thing we're going to do is we're going to find our maximum and minimum by using our amplitude. My amplitude is 4, so I'm going to go up 4 and down 4 and put in my minimum line and my maximum line. The last thing we need to do to get this thing graphed is we need to pay attention to our negatives so we know where to start and where to go. So with cosine, when you have a negative on the outside, you start at the minimum. So my first angle is 60. So I'm going to be starting at the minimum line at 60. Then we go up to the midline for the next one, then up to the maximum for the next one, down to the midline, and then finally back down to the minimum. And then you go ahead and sketch your thing on there. Now, that's the end of cosine, but remember, we're not graphing cosine. We're actually really supposed to be graphing secant. So after you graph the cosine, you're going to put in your vertical asymptotes. So we would have a vertical asymptote anywhere the cosine touches the midline. So I'm going to draw a vertical asymptote here, in here. And after that, we could just go ahead and put our secant in there. I'll do it in this red color. So it's going to look like this up here. It's going to look like this here, and then like this here. And that's it. Once again, you could extend the cycle and put more on there if you want to, but I really only need to see the first one. All right, so let's go ahead and throw one of these at you guys now. Why don't you guys try graphing a cosecant function here? So pause the video, give it a try. When you unpause it, I'll have the solution up for you. All right, guys, so there you go. The angles is the big thing I want to make sure that you got right on this one, because that's what we're working on right now, right? Should have gotten negative 1080, negative 810, negative 540, and negative 270. But all that being said, we have the midline should be at negative 4. The maximum line should be at negative 3. The minimum line should be at negative 5. Your sine wave, since it has a negative on the inside, should have started at the midline and after that gone in a downward direction before continuing the rest of the pattern. Okay, we have our vertical asymptotes wherever the sine function is touching the midline. And then we have our little blue parabola shapes, which is actually what we're trying to get for the cosecant function. All right, let's do one more set here. let's graph a tangent. All right. Now this is where things will be a little bit different because with tangent, our angles are no longer 0, 90, 180, 270, and 360. With tangent, the angles that we used to use are negative 90, negative 45, 0, 45, and 90. So with tangent, we do have a different set we're working with. So let's begin by setting the inside equal to the first angle, negative 90, and let's solve. So step 1, I'm going to add 180 on both sides. Step 2, I'm going to multiply both sides by a negative 2. The 2 is so the 2's cancel, the negative so the negatives cancel, and I'm just left with x equals negative 180. So my first angle is going to be negative 180. All right, let's do the next one. So negative x over 2 minus 180 should equal now negative 45. So I'm going to add 180 on both sides. And I believe that gives me 135. If I multiply both sides by a negative 2, I end up with 270, but it's negative 270. Now at this point, I'm not going to do any more equations. I'm just going to use the pattern once again to finish it off. You can keep doing the equations. It will work. But why do that whenever you could just use the pattern? So for instance, to get from here to here, what would we do? First of all, it's becoming more negative, so you're decreasing, so it's going to be negative. And what I'm doing is I decreased by 90 is what happened there. So to get to the third angle, we're going to decrease by 90 from that. And then to get to the fourth angle, we'll be decreased by 90 again. And then we'll decrease by 90 again. And that'll get us to our last angle. So if I take my 270 and subtract 90 from it, I get negative 360. And if I take my 360 and subtract 90 from it, I think you get negative 450. And then if we subtract 90 from that, I think we're going to get negative 540. So there's my new angles that I'm going to use to graph with. So here we go. They're all negative. So everything's going to be on the left side of the graph. So I think I'll change the way that my graph looks a little bit here, because most everything's going to be on the left side of the graph. All right. So negative 540 needs to be way over here. I don't like how I'm graphing that. I'd like it to be evenly spaced. So 1, 2, 3, 4, 5. So this one's going to be in the negative 540 because that's the smallest one, followed by negative 450, followed by negative 360, followed by negative 270, followed by negative 180. Now for tangent, what do you do now? Look at your steps. After you graph you get your graph set up with your angles on it, what do you do now? You put your vertical asymptotes in. You're going to have a vertical asymptote here at the first angle and here at the last angle. What do you do next? You plot the midpoint at the k value. The k value is whatever the number is being added out here. There isn't one, so it's 0. So my middle angle is 360. So I'm going to put my midpoint right on the x-axis because it's 0. All right. Now, this is a tangent with a negative on the inside. It's a negative x. So when that happens, tangent goes in these directions like that. Okay? So my amplitude is 1, so that means I'm going to go over 1 and up 1, over 1 and down 1, concave up, concave down, and then we finish the picture. And there it is. All right, so that's my tangent graph. All right, so let's go ahead and throw one of these at you. This will be our last one for the day. So go ahead and pause the video here and give it a try. And when you unpause it, I'll have the solution for you. All right, so first of all, make sure that your angles are good. I got these for my angles. Second of all, I put my vertical asymptotes at 45 and 135. Third of all, I got my midpoint here at 90 and up 1. My K value is 1, so at the middle angle we go up 1. All right, after that, my amplitude is a half. So, and also, since this is a negative, my cotangent is going to be going in an increasing direction like that. So, since my amplitude is a half, I go over 1 and up a half, and left 1 and down a half. And then we go ahead and connect it with the cotangent shape. All right, and that's that. So, that'll do it for today. So, hopefully that's helpful. We'll put this stuff to practice in class tomorrow. See you then.